connectivity and offers new design possibilities. 3. Circuit security. 3D integration can achieve security through obscurity. The stacked structure complicates attempts to reverse engineer the circuitry. Sensitive circuits may also be divided among layers in such a way as to obscure the function of each layer. 21. Moreover, 3D integration allows to integrate dedicated, system monitor-like features in separate layers. 3. The objective here is to implement some kind of hardware firewall for any commodity components /chips to be monitored at runtime, seeking to protect the whole electronic system against runtime attacks as well as malicious hardware modifications. Bandwidth. 3D integration allows large numbers of vertical vias between the layers. This allows construction of wide bandwidth buses between functional blocks in different layers. A typical example would be a processor and memory 3D stack, with the cache memory stacked on top of the processor. This arrangement allows a bus much wider than the typical 128 or 256 bits between the cache and processor. 22. Wide buses in turn alleviate the memory wall problem. 23. Challenges. Because this technology is new, it carries new challenges, including cost. While cost is a benefit when compared with scaling, it has also been identified as a challenge to the commercialization of 3D ICs in mainstream consumer applications. However, work is being done to address this. Although 3D technology is new and fairly complex, the cost of the manufacturing process is surprisingly straightforward when broken down into the activities that build up the entire process. By analyzing the combination of activities that lay at the base, cost drivers can be identified. Once the cost drivers are identified, it becomes a less complicated endeavor to determine where the majority of cost comes from and, more importantly, where cost has the potential to produce. 24. Yield. Each extra manufacturing step adds a risk for defects. In order for 3D ICs to be commercially viable, defects could be repaired or tolerated, or defect density can be improved. 25. 26. Heat building up within the stack must be dissipated. This is an inevitable issue as electrical proximity correlates with thermal proximity. Specific thermal hotspots must be more carefully managed. Design complexity. Taking full advantage of 3D integration requires sophisticated design techniques and new CAD tools. 27. TSV introduced overheads are large compared to gates and impact floor plans. At the 45 nm technology node, the area footprint of a 10 micrometers x 10 micrometers TSV is comparable to that of about 50 gates. 28. Furthermore, manufacturability demands landing pads and keep-out zones which further increase TSV area footprint. Depending on the technology choices, TSVs block some subset of layout resources. 28. Via first TSVs are manufactured before metallization. These occupy the device layer and result in placement obstacles. Via last TSVs are manufactured after metallization and pass through the chip. Thus, they occupy both the device and metal layers, resulting in placement and routing obstacles. While the usage of TSVs is generally expected to reduce wire length, this depends on the number of TSVs and their characteristics. 28. Also, the granularity of inter-die partitioning impacts wire length. It typically decreases for moderate blocks with 20 to 100 modules, and coarse block-level partitioning granularities, but increases for fine gate-level partitioning granularities. 28. Testing to achieve high overall yield and reduce costs. Separate testing of independent dies is essential. 26. 29. However, Tight integration between adjacent active layers in 3D ICE entails a significant amount of interconnect between different sections of the same circuit module that were partitioned to different dies. Aside from the massive overhead introduced by required TSVs, sections of such a module, for example, a multiplier, cannot be independently tested by conventional techniques. This particularly applies to timing critical paths laid out in 3D. Lack of standards. There are few standards for TSV-based 3D IC design, manufacturing, and packaging, although this issue is being addressed. 31. In addition, there are many integration options being explored, such as via last, via first, via middle winking sad smiley 32, interposers 33, or direct bonding, etc. Heterogeneous integration. Supply chain. In heterogeneously integrated systems, the delay of one part from one of the different part suppliers delays the delivery of the whole product, and so delays the revenue for each of 3D IC part suppliers. Lack of clearly defined ownership. It is unclear who should own the 3D IC integration and packaging /assembly. It could be assembly houses like ASE or the product OEMs. Design styles. Depending on partitioning granularity, different design styles can be distinguished. Gate-level integration faces multiple challenges and currently appears less practical than block-level integration. 34. Gate-level integration. This style partitions standard cells between multiple dies. It promises wire-length reduction and great flexibility. However, wire-length reduction may be undermined unless modules of certain minimal size are preserved. On the other hand, its adverse effects include the massive number of necessary TSVs for interconnects. This design style requires 3D place and route tools, which are unavailable yet. Also, partitioning a design block across multiple dies implies that it cannot be fully tested before die stacking. After die stacking, post-bond testing, a single failed die can render several good dies unusable, undermining yield. This style also amplifies the impact of process variation, especially inter-die variation. In fact, a 3D layout may yield more poorly than the same circuit laid out in 2D, contrary to the original promise of 3D IC integration. 35. Furthermore, this design style requires to redesign available intellectual property, since existing IP blocks and ED tools do not provision for 3D integration. Block-level integration. This style assigns entire design blocks to separate dies. Design blocks subsume most of netlist connectivity and are linked by a small number of global interconnects. Therefore, block-level integration promises to reduce TSV overhead. Sophisticated 3D systems combining heterogeneous dies require distinct manufacturing processes at different technology nodes for fast and low-power random logic, several memory types, analog and RF circuits, etc. Block-level integration, which allows separate and optimized manufacturing processes, thus appears crucial for 3D integration. Furthermore, this style might facilitate the transition from current 2D design towards 3D IC design. Basically, 3D-aware tools are only needed for partitioning and thermal analysis. 36. Separate dies will be designed using adapted 2D tools and 2D blocks. This is motivated by the broad availability of reliable IP blocks. It is more convenient to use available 2D IP blocks and to place the mandatory TSVs in the unoccupied space between blocks instead of redesigning IP blocks and embedding TSVs. 34. Design for testability. Structures are a key component of IP blocks and can therefore be used to facilitate testing for 3D ICs. Also, critical paths can be mostly embedded within 2D blocks, which limits the impact of TSV and inter-die variation on manufacturing yield. Finally, Modern chip design often requires last-minute engineering changes. Restricting the impact of such changes to single dies is essential to limit cost. History. Several years after the MOS integrated circuit, MOS IC, chip was first proposed by Mohammed Attila at Bell Labs in 1960. 37. The concept of a three-dimensional MOS integrated circuit was proposed by Texas Instruments researchers Robert W. Hasty, Roland E. Johnson and Edward W. Mehal in 1964. 38. In 1969. The concept of a three-dimensional MOS integrated circuit memory chip was proposed by NECA researchers Katsuhiro Onoda, Ryo Igarashi, Toshio Wada, Sho Nakanuma and Toru Tsuji. 39. ARM has made a high-density 3D logic test chip, 40, and Intel with its Foveros 3D logic chip packing is planning to ship CPUs using it. 41. Demonstrations, 1983-2012. Japan, 1983-2005. 3D ICs were first successfully demonstrated in 1980s Japan, where research and development, R&D, on 3D ICs was initiated in 1981 with the three-dimensional circuit element R&D project by the Research and Development Association for Future, New, Electron Devices. 42. There were initially two forms of 3D IC design being investigated, recrystallization and wafer bonding, with the earliest successful demonstrations using recrystallization. 11. In October 1983, a Fujitsu research team including S. Kawamura, Nobuo Sasaki and TIY successfully fabricated a three-dimensional complementary metal oxide semiconductor, CMOS, integrated circuit, using laser beam recrystallization. It consisted of a structure in which one type of transistor is fabricated directly above a transistor of the opposite type, with separate gates and an insulator in between. A double layer of silicon nitride and phosphosilicate glass, PSG, film was used as an intermediate insulating layer between the top and bottom devices. This provided a basis for realizing a multilayered 3D device composed of vertically stacked transistors, with separate E-gates and an insulating layer in between. 43. In December 1983, the same Fujitsu research team fabricated a 3D integrated circuit with a silicon-on insulator, SOI, CMOS structure. 44. The following year, they fabricated a 3D gate array with vertically stacked dual SOI /CMOS structure using beam recrystallization. 45. In 1986, Mitsubishi Electric researchers Yukie Kasekar and Tadashi Nishimura laid out the basic concepts and proposed technologies for 3D ICs. 46. 47. The following year, a Mitsubishi research team including Nishimura, A. Kasekar and Asakar University graduate Yasuo Ina fabricated an image signal processor, ISP, on a 3D IC, with an array of photosensors, CMOS A to D converters, arithmetic logic units, ALU, and shift registers arranged in a three-layer structure. 48. In 1989, an NEC research team led by Yoshio Hayashi fabricated a 3D IC with a four-layer structure using laser beam crystallization. 49. 46. In 1990, a Matsushita research team including Kei Yamazaki, Waito and Awada fabricated a parallel image signal processor on a four-layer 3D IC, with SOI, silicon-on insulator, layers formed by laser recrystallization and the four layers consisting of an optical sensor, level detector, memory, and ALU. 50. The most common form of 3D IC design is wafer bonding. 11. Wafer bonding was initially called cumulatively bonded IC, cubic, which began development in 1981 with the three-dimensional circuit element R&D project in Japan and was completed in 1990 by Yoshio Hayashi's NEC research team, who demonstrated a method where several thin film devices are bonded cumulatively, which will allow a large number of device layers. They proposed fabrication of separate devices in separate wafers, reduction in the thickness of the wafers, providing front and back leads, and connecting the thin die to each other. They used cubic technology to fabricate and test a two-active layer device in a top-to-bottom fashion, having a bulk sign MOS FET lower layer and a thinned MOS FET upper layer, and proposed CUBIC technology that could fabricate 3D ICs with more than 3 active layers. 46, 42, 51. The first 3D IC stacked chips fabricated with a through-silicon via TSV process were invented in 1980's Japan. Hitachi filed a Japanese patent in 1983, followed by Fujitsu in 1984. In 1986, a Japanese patent filed by Fujitsu described a stacked chip structure using TSV. 42. In 1989, Mitsumasa Kyoneji of Tohoku University pioneered the technique of wafer-to-wafer bonding with TSV, which he used to fabricate a 3D LSI chip in 1989. 42, 52, 53. In 1999, the Association of Super Advanced Electronics Technologies, ASET, in Japan began funding the development of 3D IC chips using TSV technology, called the RANDON High Density Electronic System Integration Technology Project. 42. 54. The term through silicon via TSV was coined by TrueSci Technologies researchers Sergei Savashchuk, O. Sinyagin, and E. Kaczynski, who proposed a TSV method for a 3D wafer-level packaging WLP solution in 2000. 55. The Kyoneji Group at Tohoku University, led by Mitsumasa Kyoneji, used TSV technology to fabricate a 3-layer memory chip in 2000, a 3-layer artificial retina chip in 2001, a 3-layer microprocessor in 2002, and a 10-layer memory chip in 2005. 52. The same year, a Stanford University research team consisting of Kaustav Banerjee, Shukri J. Sauri, Pawan Kapur and Krishna C. Saraswat presented a novel 3D chip design that exploits the vertical dimension to alleviate the interconnect-related problems and facilitates heterogeneous integration of technologies to realize a system on a chip, SoC. Design. 56, 57. In 2001, a Toshiba research team including T. Imato, M. Matsui and C. Takubo developed a system block module wafer bonding process for manufacturing 3D IC packages. 58, 59, Europe, 1988-2005. Fraunhofer and Siemens began research on 3D IC integration in 1987. 42, in 1988. They fabricated 3 CMOS IC devices based on recrystallization of polysilicon. 60. In 1997, the interchip via ICV method was developed by a Fraunhofer Siemens research team including Peter Ram, Manfred Engelert, Werner Pamler, Christoph Landesberger and Armin Klump. 61. It was a first industrial 3D IC process, based on Siemens CMOS fab wafers. A variation of that TSV process was later called TSV SLID, solid liquid interdiffusion, technology. 62. It was an approach to 3D IC design based on low-temperature wafer bonding and vertical integration of IC devices using interchip vias, which they patented. RAM went on to develop industry academic consortia for production of relevant 3D integration technologies. In the German-funded cooperative VIC project between Siemens and Fraunhofer, they demonstrated a complete industrial 3D IC stacking process, 1993-1996. With his Siemens and Fraunhofer colleagues, RAM published results showing the details of key processes such as 3D metallization, T. Grass, P. Ram, M. Engelert, Z. Gabrick, O. Spindler. First International Dielectrics for VLSI/ULSI Interconnection Metallization Conference Dumike, Santa Clara, CA, 22nd of February, 1995, and at ECT.